Welcome to Compound Semiconductor Magazine.
K-Space is renowned for its instruments that support epitaxial growth. To gain great insight into this portfolio, I'm talking to company CEO Darrell Barlett. Darrell, you started with a read instrument, the KSA 400. Since its launch, how has your read portfolio evolved in terms of its capabilities?
Yeah, good question. We started with that product 30 years ago, believe it or not, and it was an MS-DOS based product, and it has evolved obviously significantly since that time. Gives a lot of real-time monitoring capabilities, everything from growth rate of your material to in-plane lattice spacing to surface coherence. But now what's really interesting is we're using read to look at multiple azimuths during wafer rotation, and we can look at ratios of intensities along different azimuths or crystallographic directions, and tell the user what their concentration or ratio of, say, strontium to barium is during their deposition. And that has great uses, say, for quantum computing devices, STO-based quantum computing devices, and so forth. So we're able to, again, kind of lock into the rotation and take crystallographic data during rotation and then analyze that to tell you more about your growth, including concentration levels.
Thank you. What do you consider to be the most important instruments for in situ monitoring?
That's a really good question. A lot of important parameters. I would say temperature is, especially for the MBE community and probably MOCVD as well, during deposition. I'd say temperature is probably number one, right? Everything depends on your growth temperature in terms of your quality, amount of adsorption, desorption. And that's where our KSA Bandit tool has really been of great use to folks during thin film deposition, again, mainly in MBE, sputter processes, and then kind of secondarily MOCVD, where we can optically and accurately measure the wafer and the film temperature, typically down to a few tenths of a degree. And the Bandit system now has multiple temperature measurement capabilities. So you can actually measure temperature simultaneously with band edge, with fitting to black body radiation. And also, if you need to, you can resort to standard pyrometry measurement as well. So powerful tool, but I would say temperature measurement is probably number one. After that, growth rate, wafer curvature, and surface quality are important as well.
Yeah, some instruments like read, they generate patterns. Does AI have a role to play in terms of monitoring the process and adjusting growth recipes?
Yeah, so exciting, right? AI is the big buzzword in machine learning, but it absolutely has a huge role in read and in metrology in general. So just to back up a little bit, metrology in general, what we're doing is we're supplying data, obviously, and we can supply a lot of data and we can supply it in real time. Again, whether it's read images or whether it's spectral analysis for film thickness determination, we can supply a lot of data with our metrology tools, and supplying that in real time and feeding it into AI and machine learning algorithms is of utmost importance. For read, absolutely, taking data during rotation through all 360 degrees of rotation and now feeding that into AI algorithms is really important, and there's a big push for this. And we've seen our read system sales go up significantly the last 2 years, and it's almost exclusively because people want to now use AI in conjunction with the streaming read images, and use that for new material discovery, for new process control, and so forth. So yeah, very exciting times. And read is at the forefront in terms of thin film metrology.
Thank you. And for assisting process engineers growing materials by MOCVD and HVPE, what's the most you can do for them?
Yeah, good question. MOCVD is a different approach, obviously, and typically much smaller optical access in the MOCVD world. But the same tools generally apply. And with MOCVD, what we've been able to do is combine multiple technologies into one optics head, which we have to because we typically have, again, limited viewport access. So we can combine growth rate monitoring, wafer curvature and film stress, and temperature, usually in the form of emissivity corrected pyrometry, into one optics head and one tool. So we can supply those parameters in real time to the process or growth engineer for MOCVD and HPVD, and I think they find that very useful.
Can you tell me about some of the more challenging issues you've had to overcome to help your customers?
Yeah, very good question. I would say probably the most challenging issue that we've had to deal with in thin film deposition is really interfacing well and seamlessly with all the different control software that's out there, right? Every manufacturer has their own control software, they have their own interfacing. And that's a challenge to be able to feed our data into those different platforms and allow them and their users to then still perform real-time feedback and process control, right? Are we going to deal with TCP/IP? Are we going to deal with analog output and digital analog or digital output and input? And there's a lot of other technologies like IO Link and so forth, and EtherCAT coming forward. And so how do we transfer that data and that information seamlessly to all the different thin film deposition suppliers? That's a real challenge.
Yeah. What are your plans for the next year or so? I mean, are there new products in the pipeline?
Yeah, really good question again. Appreciate that. I'd say right now the biggest plan or the most important plan is to really make our existing product line for thin film deposition seamless for AI so that we can make it easy to feed and stream that data into AI and to machine learning algorithms. And this is new for us as well. We're not experts in AI or ML, but we're tackling it now, and I think that's one of the biggest challenges for us currently, and where we want to move forward. We're also trying to add another temperature measurement technique to our bandit system. Like I mentioned before, we can do band edge temperature, pyrometry, and blackbody measurement, but there's other materials where kind of none of those techniques work really well. Some of the small band gaps, some of the highly doped materials, none of those techniques work really well. So we're adding another, what they call an E1 inflection point measurement. It's a spectral reflectivity measurement. We're adding it to Bandit to tackle some of those tougher materials and still get a good optical measurement of temperature. So those are a few of the things we have on the horizon.
Thanks, Darryl. Been great talking to you.
Oh, you too. Appreciate it very much.